solving a differential equation involving a Dirac delta function. Okay, we're going to solve this initial value problem. I have the second derivative of y minus 2 times the first derivative of y is equal to 1 plus delta of t minus 2, and my initial values are y of 0 equals 0 and y prime of 0 is equal to 0. Down here at the bottom of the screen I have some basic Laplace transforms. We want to start by applying the Laplace transform to each term in the equation. And that'll give us a Laplace of the second derivative of y minus 2. Notice that I've taken out the coefficient. Minus 2 times the Laplace of y prime equals the Laplace of 1 plus the Laplace of delta of t minus 2. So the Laplace of the second derivative, we look in our formulas. You can see the Laplace of the second derivative is s squared times the Laplace of y minus s times y of 0 minus y prime of 0. The Laplace of y is the same thing as y of s. So you get s squared times y of s minus s times y of 0 minus y prime of 0. And we'll replace these values y of 0 and y prime of 0 with their initial values on the next step. So the Laplace of my second term, I'm going to have the negative 2 times the Laplace of y prime. Here's my formula for the Laplace of y prime. So I get negative 2 times s times y of s minus y of 0. Then on the right side of the equation equals the Laplace of 1. Here's my Laplace of 1 is 1 over s equals 1 over s plus the Laplace of delta of t minus 2. And we also have that in our formula sheet. See, here's our delta function. Laplace of delta of t minus c is e to the negative sc. So in this case, it's going to give us plus e to the negative 2s. Okay, so now let's go back and fill in our initial values. We know that y of 0 is equal to 0. That's going to cancel out this second term and the last term on the left side of the equation. And y prime of 0 is 1. So we're going to get a 1 here. So there's my y of 0 is 0. Y prime of 0 is 1. Here again y of 0 is 0. And the right side doesn't change. So let me cancel out those 0 terms. And I get s squared y of s minus 1 minus 2s y of s equals 1 over s plus e to the negative 2s. Just so that I don't get confused with multiplication and function notation, I'm going to rewrite this y of s notation as just y. So we get s squared y minus 1 minus 2sy equals 1 over s plus e to the negative 2s. And there we finished applying the Laplace transform to each term in the equation. Now we want to work the equation so that we can get the y on one side of the equation and everything else on the other side. And then apply the inverse Laplace transform to get the solution to the initial value problem. So let's work to solve for y. Okay, so here we have our equation. and we want to solve for y, which means we want to get the y by itself on one side of the equation and everything else on the other side. I'm going to start by adding 1 to each side of the equation. That's going to bring the 1 over to the right side. I put the 1 in front. And then to solve for y, I need to factor out the y. It's going to give me y times s squared minus 2s. And then I can solve for y by dividing both sides by s squared minus 2s. Before I do that, let me combine these two terms on the right side. When I add 1 plus 1 over s, 1, remember, is s over s. So you get s plus 1 over s. And now divide both sides by s squared minus 2s. And that's going to put an s squared minus 2s here in the denominator. And it's also going to give me e to the negative 2s over s squared minus 2s. Notice that s squared minus 2s can be factored. You could factor out the s. And factoring out the s will give you an s squared here on the first denominator times s minus 2. And you get the s times s minus 2 on the second fraction. Notice that I kept these two fractions separate because the second one involved that exponential e to the negative 2s. And when we apply the inverse transform, we're going to get a unit step function. So I want that function kept separate from our traditional inverse Laplace transform. But what we'll have to do before we apply the inverse Laplace transform is use partial fraction decomposition for both of these fractions to write each of the fractions as a sum of simpler fractions. So let's get ready to take the inverse Laplace transform. Again, we're going to do partial fraction decomposition. I'll start with this first fraction, and I want to write it as a sum of simpler fractions. We could set this up as, because my denominator has s squared times s minus 2, with that s squared, you'd set it up as a over s plus b over s squared, and then with the c over the s minus 2, you get c over s minus 2. And our goal is to solve for a, b, and c so that this is a true statement. You can do that by multiplying through by the common denominator, which is s squared times s minus 2. And that'll cancel out the it'll cancel out the denominator on the left side to leave you with s plus 1. On the right side, on the first term, the s will cancel, and you'll get a times s minus 2. For the second term, the s squared will cancel, and you'll get b times s minus 2. And on the third term, the s minus 2 cancels, and you get cs squared. Okay, so here we have a polynomial equation that we can solve. I'm going to solve this by equating like terms. I'll start by simplifying on the right side by distributing to remove parentheses. So here when I multiply by as, I get as squared minus 2as. And then distributing through by b, you get bs minus 2b, and then I have plus cs squared. Combine like terms. My s squared terms are a s squared plus cx s squared, a plus c s squared. I have my s terms, negative 2a s plus bs, gives me negative 2a plus b times s, and that leaves me with negative 2b. And then when I equate the coefficients on my s squared terms, on the right side I have a plus c. On the left side there's not an s squared term, so a plus c has to be equal to 0. For my s terms, I have negative 2a plus b is equal to 1s. Negative 2a plus b equals 1. And for my constant term, I have negative 2b is equal to 1. Negative 2b equals 1. So that constant term tells me that b is equal to negative 1/2. And then I can use b equals negative 1/2 to solve for a. If I add 1/2 to both sides, 1/2 plus 1 is 3/2. It'll give me negative 2a equals 3/2. Divide by negative 2, and you get a equals negative 3/4. And then knowing that a is negative 3/4, I can solve for c. Notice that c is equal to negative a. And if a is negative 3/4, then c is 3/4. So this first fraction, when you break it up into a sum of simpler fractions and solve for a, b, and c, we get a is negative 3/4, b is negative 1/2, c is 3/4, and that's going to give me negative 3/4 over s plus negative 1/2 over s squared plus 3/4 over s minus 2 is equal to s plus 1 over s squared times s minus 2. Okay, so now let's look at our second fraction and do the same thing. So on the second fraction, I'm going to separate out the exponential part and apply partial fraction decomposition to just the 1 over s times s minus 2. And that's going to give me two fractions, a over s plus b over s minus 2, multiplied by the common denominator. And again, each denominator will cancel out. On the left side, we're left with 1. On the right side, the s cancels. It'll leave me with a times s minus 2. And on that last term, the s minus 2 cancels, and you're left with b times s. So simplify by distributing through by the a to get as minus 2a plus bs, and then combine like terms so that we have a plus bs minus 2a. When you equate the coefficients, on the s terms, we have a plus b is equal to 0. Again, because there's no s term on the left side. And for the constant term, you get negative 2a is equal to 1. So I use that second equation to solve for a. You get a equals negative 1/2. And then because a plus b equals 1, we know that b is equal to negative a. And if a is negative 1/2, then negative a is going to be 1/2. So b is 1/2, a is negative 1/2. And this second fraction, 1 over s times s minus 2, is going to become negative 1/2 over s plus 1/2 over s minus 2. When you add the exponential part to that, again, I just kept that factored out. You still get that same partial fraction decomposition, but times e to the negative 2s. Okay, so now we're ready to do our inverse Laplace transform. We've rewritten both fractions on the right side into simpler fractions. So now apply the inverse Laplace transform to each term. You get the inverse Laplace of y equals, here just pull out the coefficient of each term, negative 3/4 times the inverse Laplace of 1 over s minus 1/2 times the inverse Laplace of 1 over s squared plus 3/4 times the inverse Laplace of 1 over s minus 2. Here I broke this up into two terms. You watch, I'm going to bring it back together in just a minute. But I have minus 1/2 times the inverse Laplace of 1 over s e to the negative 2s, and then plus 1/2 times the inverse Laplace of 1 over s minus 2 e to the negative 2s. Okay, so match up the inverse Laplaces with each one of our formulas, and you'll see that the inverse Laplace of 1 over s, that's this one right here, is 1. So my first term becomes negative 3/4 times 1. Of course, the inverse Laplace of y is your y of t. So I get y of t equals negative 3/4 times 1. On the second term, the inverse Laplace of 1 over s squared, that's this one right here, will give me t. So this second term will become negative 1/2 t. On this third term, the inverse Laplace of 1 over s minus 2, you would find this one right here. 1 over s minus a gives you e to the at when you apply the inverse Laplace. So I'm going to get e to the 2t, 3/4 e to the 2t. On the right side, when we have this e to the negative 2s, that's going to give us our unit step function. So they both have e to the negative 2s. It's going to give you the unit step function. U to the t minus 2. And is going to require that our function inside, once we apply the inverse Laplace, we're going to have to shift 2 units. So when we find the inverse Laplace, we're going to have to shift the t to t minus 2. So notice here I also factored out the negative 1/2. So I'm actually doing a couple of things here. I applied the unit step function to both of these because they had the same shift, and that gave me u to the u of t minus 2. I factored out negative 1/2 because I saw that they each had a 1/2 in common. And that's going to give me the inverse Laplace of 1 over s, where you have to take into account the shift from t to t minus 2, and then minus, because I'm factoring out a minus here, the inverse Laplace of 1 over s minus 2, where I'm shifting t to t minus 2. Okay, so now when you look up the inverse Laplace of 1 over s, that's just 1. And 1 doesn't involve t at all, so you don't have to worry about a shift here. That just becomes a 1. And then here, this is our exponential. The inverse Laplace of 1 over s minus 2 is going to be e to the 2t, but we'll replace the t with t minus 2. So watch, I have a negative 1/2, my unit step function of t minus 2, and then here the inverse Laplace of 1 over s is 1, minus the inverse Laplace of 1 over s minus 2 is e to the 2t, but you want to replace t with t minus 2. And there's your answer.